Good afternoon, ladies and gentlemen. Thank you for the opportunity to participate in WIS Second International Summer School. Let me introduce the presentation with following topic: Kinetics of absorption and photoluminescence of cadmium selenide nanoparticles in the cadmium octanoate matrix by pulse laser excitation. In this work, we study nanocomposites based on cadmium octanoate matrix. First of all, a few words about this matrix. Cadmium octanoate belongs to the class of ionic liquid crystals, namely metal alkanoates. This is the general formula of these metal alkanoates. The interest in the study of these ionic liquid crystals has grown due to their unique physical and chemical properties. For example, ionic liquid crystals have a wide interval of mesophase existence, a high thermal stability, and its own ionic conductivity. Metal alkanoates, besides metal alkanoates, can maybe a good matrices, universal matrices for organic and inorganic impurities, for metal and semiconductor nanoparticles. We consider cadmium octanoate in two different phases. First of all, cadmium octanoate forms thermotropic ionic liquid crystal at temperature 1908 Celsius degrees. And it is very interesting that it keeps the liquid crystal ordering after being cooled to the room temperature. And cadmium selenide nanocrystals were successfully synthesized in this matrix in the Institute of General and Inorganic Chemistry in Kiev. Primarily our goal was the investigation of shape, size, and structure, crystal structure of these nanocrystals. The synthesized polycrystalline powder was used for preparation of the samples of two kinds, of two types of the samples. The polycrystalline powder was the cadmium selenide nanoparticles were synthesized in this matrix at different temperatures and in different mesophases. So we prepared two types of the samples. The synthesized prepared samples was investigated by the transmission electron microscopy, and the analysis of obtained images show that in this first sample we observe the nanocrystals with characteristic size of about 4 nanometers. And two types of the nanocrystals were observed in the second sample, 4 nanometers and 8 nanometers. Here I present absorption spectra of nanocomposites, which are depicted by the curves 1 and 2. Matrix, cadmium octanoate, transparent or don't absorb the light in this visible spectrum region. The absorption spectra of nanocomposites characterized by two well-resolved bands, absorption bands, which are called doublets. First maximum in this doublet corresponds to electron-heavy hole transition, and the second maximum corresponds to the electron-light hole transition. you can see that the quantum confinement effect is observed in this case. All absorption bands are shifted to the high energy region relatively to the band gap of the bulk cadmium selenide crystal. Some words about with doublet. Early, only one absorption doublets were observed for cadmium selenide, and their shape was close to spherical. The same character of absorption spectra were observed by our colleagues, see below, for colloidal nanoplatelets. So this character of absorption spectrum means that the shape of our nanoparticles is close to nanoplatelet. This is a schematic model of our platelets. Depicted the thickness of the platelets. And using the absorption spectra, we can calculate the thickness of these nanoplatelets. B and C is lateral sizes of nanoplatelets obtained from TEM images, transmission electron microscopy images. And the obtained values are for the first sample 1.9 nanometers and 2.3 nanometers for the second sample. It was shown that cadmium selenide nanoparticles can form zinc blende, rock salt or Wurtzitz crystal structures. Electron diffraction confirmed the crystallinity of our nanoparticles and the and their composition, nanocomposites. And from electron diffraction, we calculate interplanar spacing for cadmium selenide. The obtained values for the sample 2 are in a good agreement with one obtained early for hexagonal structure. Let's see below the reference. And so the crystal structure for our nanoparticles is close to hexagonal structure, Wurtzitz structure. Here we present the spectra obtained for the sample of the first type. The absorption spectra depicted by the dashed curve, and the photoluminescence spectra obtained photoluminescence spectra depicted by the red color, and other curves are photoluminescence excitation spectra. Let's consider the photoluminescence spectrum. It consists of the sharp peak, a wide band at 520 nanometers, and long wave shoulder. First sharp peaks corresponds to the A-exciton recombination, a combination of 3 excitons. And the second other wide broad band and wavelength shoulder correspond to the localization to the exciton localizations. You can see the values of photoluminescence decay time, fast and mono-exponential character of the first, in the first case, supports the suggestion that it corresponds to the exciton recombination. Other long wavelength peaks corresponds to the We have two components, B exponential character of delay kinetics, time delay kinetics, and with can be assigned to the presence of two types of surface in our surface of two kinds of size for exciton localization and two kinds of surface of nanoplatelets. For example, a flat surface and the end surface of these nanoplatelets. The photoluminescence excitation spectra have the similar structure but different intensities. Different structure confirm that all photoluminescence peaks are connected with the same radiative object, and mainly nanoparticles, cadmium selenide nanoparticles. And as you can see, with maximums corresponds to the absorption bands. So we assign with peaks to A exciton to the transition electron light heavy hole and electron light hole. The spectra for the sample 2 are basically similar with the first, only all features are shifted to the long wavelength region. We also investigate the optical density variation after under the strong pulse irradiation. And we observe the decreases of optical density under the pulse, so transient induced transparency is observed. Let's summarize the results. The quasi-two-dimensional structure of cadmium selenide particles was determined, and the linear size of cadmium selenide nanoparticles were evaluated. The crystal structure is close to the spherical with nanoplatelets, and detailed analysis of photoluminescence spectra confirm the presence of nanoplatelets, and the obtained samples of the first type are the most monodisperse. Obviously, that the synthesis of the cadmium selenide particles in the liquid crystalline phase is more prospective. Thank you for attention.
What was the size of the nanoparticles?
Size? We have two characteristic size. Lateral size, about 4 to 8 nanometers, and the thickness, about 2 nanometers.
Another question? If you measure the size to different technique, I mean IFM, SAM, or whatever?
Once more, please. No.
How did you measure the size of the particles with another technique? IFM,
Яким способом змірювали розміри частинок? Яким способом?
The lateral sizes were determined from. The lateral sizes from. Lateral size were estimated, obtained from the TEM images. The thickness of this nanoplatelet, they are determined from the absorption spectra as one of the linear size of quantum box. Because we we observe a quantum confinement effect.
Okay. Another question? Okay.
What about the stability of this quantum process? For the stable
What the stability of your particles?
And so this sample was good during the measurements. I
Okay. Thank you very much again.